Welcome to another session of our CIF seminars. I'm really happy to have Nikita here today. I met Nikita, I think, in 2019 or 2020 at a Safety Critical Systems Club event in London, I believe, which was about safety security integration. And now today she's going to talk about the safety security co-assurance and the rise of the robots and whether we have to be scared. Nikita is from the University of York. I think you finished your PhD this year, right? A couple of months ago.
Last year.
Last year. All right, cool. So that's going to be awesome, and I'm really looking forward to your talk. I just want to say that this is the last CIF seminar, most likely before the summer break, unless someone comes up with the fundamental solution to all legal and social problems to computer security and privacy. We are probably not going to have another talk before September. Instead, we're going to hibernate for a while and enjoy the summer and have a long-needed vacation. So, yeah, Nikita, the floor is yours.
Great, thank you. And like any good British person, I'd like to begin with an apology. I've got way too many slides here, so I'll be going through some of them quite quickly. But hopefully I'll get across the key technical and socio-technical issues with particularly co-assurance of safety and security for robotic and autonomous systems. So the agenda for this meeting is to quickly look at some of the state-of-the-art techniques, standards and guidelines for co-assurance, and from those get what the remaining technical and socio-technical challenges are. I'll talk briefly about the safety security assurance framework that I developed as part of my PhD and have been applying to RAS systems, so robotic and autonomous systems. And then just a discussion about the ongoing work and what we're doing going forward in the Assuring Autonomy International Programme. So just to give some context to the problem that I've been looking at between safety and security, I'm going to use the ALARP concept. So in the UK, we've got, in UK law, health and safety law, there's this concept that risks should be as low as reasonably practicable. And what that means is that it's either the organization, company, whoever's posing the risk or gains the most from that risk being present, it's their responsibility to systematically reduce risk and to show how they've done it. So over the years, we've developed in different domains an idea of what an acceptable risk is. So this is well established in aerospace, for example, as well as in rail. So the idea is you identify what the risks are for a system and then either mitigate, redesign, or put in operational or behavioral mitigations for the system and reduce risk that way. I've borrowed the scientific concept of a confidence window here to demonstrate that even though we reduce risk, there's still a region of uncertainty, and we make that window smaller through the techniques we use, the processes that we have for assurance, and the arguments that we make. And those also are quite mature for the safety domain. So for example, in aerospace, we have the standard ARP 4754A, which has a well-established process and activities that we need to perform at different stages of system development. But both the safety and security interaction and autonomy pose two problems to this kind of ideology around risk. The first is that we may not actually know what the risks are in reality. For security, this is because there's an intelligent adversary, so we are unsure about all of the potential risks that may contribute to a safety hazard. And for autonomy, it's because once the machine learning algorithm is trained, the output is deterministic. There's uncertainty for the connections that are made within the algorithm itself. So I'm thinking here about potentially a neural network, for example. So that's the first problem that the uncertainty introduced by security and/or autonomy introduces. The second one is that we don't have the processes, activities, and argument structures that we do have for traditional systems. So whilst even if we did identify the risks correctly, what it means is that our confidence window may be much larger and may take us into that unacceptable region of risk, regardless of if we've actually identified the correct level of risk. So with those two problems in mind, we need to solve that problem by introducing, first of all, new processes and activities to be able to gain confidence in the risk analyses and reduction that we do, but also new ways of identifying risks accurately so that we can know that we've identified the risks for a system. So the existing approaches for traditional, I'm going to make the distinction between autonomous systems and what I'm going to be calling traditional systems, so ones without autonomy or freedom of decision making. There are several standards and guidelines, and here I've just put up a summary of a few of those, and they're divided into three sections. The first is the safety standards. So I've already mentioned the aerospace standard. There's security standards. A lot of them are based on sort of generalized standards, such as common criteria and the NIST 800 series. But then emerging are new standards and guidelines, such as the IET Code of Practice for Cybersecurity and Safety, which provide organizations with guidelines on how to align or integrate safety and security at multiple levels of abstraction. So the Code of Practice, for example, is at organizational and governance level, whereas 63069 deals with the system and component level alignment. I'll give a few more detailed examples of these standards in a minute. So just to, for those of you who are unfamiliar, our baseline safety standard is 61508, and this originated in the industrial control domain. But what it is a set of 7 documents or 7 parts to the standard, and the most interesting or the main parts are part 1, which gives you context for the overall standard, part 2, which predominantly deals with the hardware, and part 3, which predominantly deals with the software. So what it does is it lists the process, activities, and some of the requirements that safety practitioners need to provide in order to argue that their system is safe. So that's our baseline safety standard. Our baseline security standard that we'll be using is the common criteria. This doesn't present a process for arguing security, but what it does is that it lists the structure and requirements for different elements. So the important thing is here that you can create what's called protection profiles for particular systems based on the requirements of that system. So those are the two, as I said, baseline safety and security standards that we'll be using. The IET Code of Practice that I mentioned earlier provides quite high-level principles for the alignment of safety and security. So what you can see here is things like accountability for the organization's operation. It talks about the scope of interest, the system of interest. So where that fits into our baseline standards is that it sits on top of it. So it deals with the socio-technical factors of aligning those those two attributes. Another joint standard is the PAS 1885 from automotive. And what this does, again, it deals with the socio-technical. As you can see here, people, process, physical and technical in the middle. But it also starts to look at the overlapping sub-attributes of safety and security. And here we can see CIA is included here, resilience, and authenticity. So this goes one step lower than the code of practice. The last example of an alignment standard or guidance document that we'll be looking at is from aerospace, and that's DO326A. And what we see here is we've got the safety process from the safety standard, so ARP 4754 here. We've got the system development process, which is also included in the safety standard. And then we've got a security process, which was specifically developed to align with those other two processes. But if you look closely at the flow of information as it's depicted here, you'll see that there's no direct flow of information from the security process back to the safety process. It's all through the system development process. So what I would class this standard as is a security-informed safety standard. And whilst this is good for a domain like aerospace, what this implicitly says is that safety almost always takes precedent over security, which may not be the case for all systems. So whilst this is a very good standard for aligning safety and security, there are still some holes when dealing with the bidirectional interaction of safety and security. So we've just covered some of the standards. They've got a lot of benefits and limitations to both sides, or different ways of bringing the two together. But I don't have enough time to go through each of those, but hopefully I've demonstrated some of the key approaches and some of the key benefits and limitations of the existing standards that are out there. So as well as standards and guidelines, there are some approaches which are derived from traditional safety and security approaches. So I've divided them into 4 categories here: risk analysis or hazard analysis, the mitigations and controls approaches, architectural or systems approaches, and assurance approaches. So just to give, again, a bit more detail into what I'm talking about when I say these approaches, we'll look at just a few of these categories. So the first is looking at risk analyses. The first way that people have aligned safety and security, or done a co-analysis for safety and security, is using bow tie analysis. So bow tie is quite elegant in the way that it brings together safety and security, because it has the idea of some kind of contributor leading to a risk, and that risk having a consequence. So the occurrence of that risk having a consequence. But in addition, you have prevention mechanisms and recovery mechanisms. And this idea or paradigm fits for both safety and security. So what it means is that in the literature, people have combined, for example, security vulnerabilities or attacks leading to a safety risk that has particular consequences, or the other way round, a safety event, a safety consequence leading to a security vulnerability which has a particular consequence. So as I said, it's quite elegant in that you can combine the two and create those relationships between them. Another way of combining the two is using systems theoretic process analysis, which originates in the safety domain. And the idea for the safety analysis of STPA is using control structures to understand what hazards can occur through these control instructions and feedback. But what happens with STPA-SEC is that they use a well-known security analysis stride to superimpose and find out what are the security risks that can arise through these flows or control flows. The last example of hazard analysis or hazard co-analysis that I've selected is FMEVA. So similar to STPA-SEC, they've superimposed a threat analysis on a traditional safety analysis. So here you can see, usually it's FMEA, so failure modes and effects analysis. And here they've added the vulnerabilities aspect to it. So they take the failure cause and the vulnerability, they derive the effects, the severity and the likelihood of that happening, and they can come up with a criticality for that. So this is a very good approach to safety security alignment because it allows the safety and security practitioners to have the same kind of structure to reason about risk, and they can use their expertise to contribute to this kind of analysis. One of the major drawbacks is that FMEA for safety and FMEVA for the combined analysis is heavily text-based. So capturing these in a way that can be dynamic and change during the lifetime of the system is quite problematic and requires a lot of resource, so expertise and time to be able to come up with accurate and useful representations of sort of consequence criticalities. Another guide word example, which isn't derived from a safety or security analysis, this is completely created for the alignment of safety and security, is using data security properties from NIST 853 and the data safety properties from the Safety Critical Systems Club data safety guidance. And what they've done is linked particular sub-attributes. So before, when I was talking about the linking of CIA attributes, so what they've done is taken, for example, confidentiality, integrity, and availability, and said that any consequences that are related to those three have an overlap with safety and security. This obviously has a lot of advantages because, again, it can guide experts to be able to find those links more efficiently. But one of the drawbacks is that, again, it is very text-based and quite resource-intensive, but does structure the thinking between the two teams and bring them together. I am going quite fast. I haven't seen any questions in the chat yet, but please do feel free to stop me at any point if you wanted any clarification on a point I've made. So the next category of approaches that we'll be looking at is the architectural or system-based categories. The first one that we're looking at is ATAM, so the architecture trade-off analysis method. So this is an approach that has 8 steps, and again is a structured way of bringing stakeholders together with their expertise and trading off different system architectures in order to optimize the attribute that they're responsible for. So this isn't just for safety and security, it could be for maintainability, reliability, the stakeholders in this group include systems engineers, architects, safety security practitioners. So it is quite a big group that comes together, performs the analysis, and as an output of this analysis, you get the sensitivity points. So the points in the architecture where a small change would have a big implication on one of the attributes, the trade-off points where decisions need to be made, and the output risks. So risks in this sense is about the architecture and its performance rather than our traditional understanding of what safety and security risks are. Another approach that relies on the system or architecture is SSAF, and SSAF makes use of an approach called dependability deviation analysis. And the idea behind the SSAF approach is that you have safety and security information as an input, but also the operational requirements of the system. Again, experts are brought together to perform unified activities. Those update the architectural model and the risk models. Again, there's a trade-off or decision point for the design process, and we get module functional properties and also a modular safety case, or the beginning of a modular safety case or security case based on certain properties. And then the objective of SSAF is to be able to have some kind of modular certification process where contracts are defined between the safety and security. And that can enable safety certification and security accreditation, particularly for aircraft systems. But also we can have operational acceptance. So I haven't gone through each of the categories just because of the restrictions on time, but talking through the details of just some of those approaches, what we've seen is that actually, I've been talking about safety and security risk as if they're well-defined and well-accepted, but there's actually still a lack of unifying language. And in most settings, safety has a very strict definition. So the likelihood and severity of some harm occurring, whereas security has a wider definition that does incorporate things like business objectives and also operational and mission risks. So what still needs to occur is some kind of unification of language or acceptance of a shared dictionary or ontology. I've talked about some of the kinds of complexity that can occur during analysis and co-assurance. One of the things that I haven't brought out as clearly yet is that a distinguishing factor for security is the intent of the attacker. So many of the approaches that I've talked about sort of are context-free. And what I mean by that is that in order to bound the uncertainty and bound that complexity, they make assumptions about what the attacker is capable of and the resources that they have available to them. So, for example, STPA SEC does make some of those examples, as does FMEVA. And I have talked about how to incorporate different types of risk. And another thing that I haven't quite made explicit yet is this idea of model divergence. So when I was talking about the approaches being heavily text-based, that becomes a problem when risks are updated during the operation of a system, because being able to incorporate that new information becomes a lot more difficult, because those approaches are not conducive to incremental change. So what might happen is that the risk models that we have may diverge from the actual system models that we have, or diverge from each other, so the safety and security parts of those models. But as well as the technical uncertainties that are introduced by these approaches, we also have some socio-technical uncertainties. So underlying this lack of unifying language is actually a lack of unifying philosophy. So whereas security values things like defenses such as security through obscurity, they have a very strong concept of risk acceptance and risk appetite. On the safety side, often in our standards, we're given what our risk appetite is. So we can take that for granted and work from that point. So in order to bring the two together, we need some kind of way of unifying these philosophies and not just unifying them at the technical level. Because a lack of philosophy could mean that it's, sorry, there's just a question that's, yes, absolutely. So in the comments, there's also a mention of patching for security and changing as soon as possible. So there's several philosophical and socio-technical uncertainties that have the potential to undermine even the technical analyses that we do. So it's unacceptable, or we can have only very little confidence to separate those and say, well, actually, we've got a unified model, therefore safety and security is unified. That would need a lot more support and a better way to approach making that argument. And that's where the framework that I developed comes in. It is a two-part framework that looks at both the technical and socio-technical parts of the co-assurance problem. On a conceptual level, this is what the safety security assurance framework looks like. It's based on something called independent co-assurance. So the idea is to keep safety and security separate. So keep the discipline separate, the activity separate, so that we can make the most of those expertise. But the only reason that makes this work, and that is fundamental, is having these synchronization points throughout the lifetime of the system. So not only through design and decomposition, but through integration and test, and through operation, maintenance, and even decommissioning. So what happens at these synchronization points is that information is exchanged via the system models or via analyses to the different teams. And this could be a joint analysis or transfer of a particular model. What is difficult about this approach is that some work needs to be done upfront to be able to establish the information needs of both safety and security in order to establish these interaction points. But one of the advantages that we have, or one of the head starts that we have, is some of the standards and guidelines that I mentioned before, they are actually describing synchronization points. So in the ARP DO326 interaction process model that I showed, that is describing what information needs to go from security to safety, but not the other way around. So the main thing that we need to take away from this diagram is that independent co-assurance is about getting the right information to the right people at the right time, and that's throughout the lifetime of the system. So how does this actually work in the real world, in practical terms? Going back to that problem that I mentioned, or those two problems that I mentioned earlier, how do we make sure that we're identifying the right levels of risk and that we can be confident once we've performed the analyses? Well, the first way to structure our thinking, this is a GSN diagram, and whilst it looks quite complicated, it really isn't. All it is a top-level goal about safety and security alignment, and we call this a risk-based structure. So it's based on a strategy where we say we have identified all of the interaction risks between safety and security for a system. And then for each of those interaction risks, we have a requirement to address those. So whereas talking about the behavioral or operational requirements or some kind of control, these are the requirements that we have to address each of these risks. And then as a leaf node, a solution, we have a link to evidence that that has been addressed. So just breaking that down a little further, this context box of that we've identified a sufficient number of interaction risks, it's quite simple to write down, but actually very difficult to discover. And as we've seen already, we can use things like FMEVA, STPA-SEC, the CRAF framework to be able to identify these risks. And what I mean by interaction risks, just to be clear, is where a risk originates from a separate domain. So the important thing to understand here is that actually there may be risks that we haven't modeled that are interaction risks. So where we say sufficient, that is a qualification that is actually really important and that needs to be defined in order to have confidence in this overall structure. Because if an insufficient number of interaction risks have been identified, then this argument would be a good start, but wouldn't be enough to have confidence in co-assurance. So a way to formally or semi-formally model these interaction risks is by using this condition-to-condition relationship model, this causal model. And what this says is that actually any modeled condition that we have for our system, this is just a subset to illustrate the point, is connected to other conditions in our risk model through a particular type of relationship. So I'll just quickly talk through the different types of relationships. So linear can be thought of as the reasons Swiss cheese model. So the idea that conditions are linked sequentially, one after the other, and they impact in series. Complex recognizes that actually there can be multiple relationships to particular consequences and multiple relationships from a particular consequence to create new risks. And then emergent is closer to the causal model that STPA uses. So the idea that actually a lot of hazards are an emergent property of what happens in the system and can't be broken down or reduced to sequential incidents. So this is what we're using as our base understanding of what the causal model between safety and security is. So that's what we can start to use, not only to identify what those interaction risks are, but to be able to provide evidence to show that we've identified them and mitigated them. And as part of my PhD, that's one of the things that I've tried to do. I've tried to create patterns for example, linking safety requirements and security requirements, describing the nature of that relationship, and then providing the types of methods that you can use to be able to show that to demonstrate that you've made that trade-off. And as you can see, there is a range of conditions that can be linked, and also a range of relationships between those conditions. Now, I'll just caveat that now by saying that this is not a comprehensive list. I'm not making any claims to completeness of this list, but what this does provide is a good starting point and a catalogue to be able to contextualize what's happening at those synchronization points that I talked about before, how to model and capture that information so that both safety and security practitioners can understand what's happening with the information exchange. But what I was talking about with the link patterns is purely on a syntactic level. So the way I like to think about it is it tells you how to draw the boxes and the lines between them, but it doesn't talk about what's in the boxes. So also as part of my research, what I've developed is looking at the sub-attribute links. So similar to CRAF, so the cyber risk assessment framework that used CIA to link safety and security. The same here, I've broken down what the sub-attributes of CIA are. And that's enabled me to be able to do things like, if there is a hazard related to, for example, the communication of a safety critical piece of information, then we can confidently say for that same system that any network vulnerabilities are related to that hazard, because those network vulnerabilities have the ability to undermine or stop that safety critical piece of information from being delivered. So what we can end up doing is linking so DDoS vulnerabilities to that particular hazard. And then in the safety argument itself, or the co-assurance argument itself, what we can then do is start to break down according to each of those sub-attributes and make specific claims related to the sub-attributes. So here I've just taken or developed the leg of the argument related to resource use. You'd have multiple legs of an argument related here, but here we have an argument over the requirements interactions for resource use, and you might be able to show that using BBN, for example, but I've also seen it being done in combining fault trees and attack trees. It's not so much what you provide as evidence, but what the link represents or what you're arguing over to demonstrate. So we've got the semantic part shown here, but also the syntactic part shown in the link patterns. So I've taken you through a whistle-stop tour of not only what the existing approaches are, but also what SSAF brings to the table. But it might be a little unclear still, so I've got a quick example using an autonomous, or rather starting off with a traditional infusion pump, but then speaking about the additional hazards and risks posed by an autonomous infusion pump. Are there any questions at this point?
Plenty from my side, but I think I'll bring them up later after your example.
Okay, great. I can do that. So the case study that we'll be using is actually a very simple one. So this is the one-touch ping infusion pump, insulin pump, sorry, and it consists of two parts. This part is the remote, where a diabetic patient inputs the last meal that they had. And this part is a delivery system that's connected intravenously to the diabetic patient. So the diabetic patient would put in the last meal of, let's say, I don't know, fish and chips, and that would deliver the correct amount of insulin required to balance that meal out. And this is a just high-level block diagram of how the system works. So to be able to co-assure this on a technical level, SSAF provides a technical risk process, and it consists of 5 steps. The first step is establishing a shared language or shared ontology and those synchronization points that I mentioned before. The second and third steps are where the safety and security disciplines separate and go and do their separate assurance activities. So whether or not that is single domain analyses, argumentation, whatever those processes are. And then step 4 and 5 are when they come back together and link those artifacts or create those co-assurance links. And then step 5 is ongoing, so either through system development or through operation maintenance and decommissioning. So for the first step, for this particular example, what we have is we've got 2 standards. So AAMITIR 57 is guidance from the American Association for Medical Instrumentation, I believe. This is guidance produced specifically to map onto ISO 14971. So this is safety of medical devices. So what they do is they define the language and also some interaction points, so some synchronization points where they expect information to be exchanged. So a developer creating this medical device could use these 2 standards, or the standard and the guidance, as a starting point to be able to define not only the ontology, but also the synchronization points. As you see here, though, there's only 3 synchronization points, which I would argue is insufficient for this kind of system. So in addition to using these synchronization points that are defined, they will need to define additional information exchange points and define what is expected at those. So that's step 1 of the SSAF process. Steps 2 and 3, as I said, is where safety and security separate and go and do the separate activities. So I've got an example of what's happening on the safety side as far as the argument. And this is just a general risk-based argument for the insulin pump. What we have at the top as a top-level claim is that the insulin pump is adequately safe. And then again, a risk-based argument that we've identified the risks and that we're going to argue over each of the risks. So we have traumatic injury, biological or chemical contamination, infusion, and incorrect therapy. And I've just developed the infusion delivery error. And what that breaks down into is hypo and hyperglycemia, so too much insulin and too little insulin. And again, arguing over each of the ways that too much insulin can occur, so hypoglycemia can occur. And one of the ways that that can occur is through excess insulin during meal correction. So when a diabetic patient puts into the remote, the delivery system could send too much insulin into the patient. And then here on this last strategy, so ST2, is the argument over the different ways that excess insulin can be delivered. And that can be uncommanded or commanded. And just as an example, this is a toy example. The actual case is a lot more complex than this. A way that you might be able to demonstrate that commanded infusion is adequately mitigated is by using a fault tree. So I'll go quickly to the fault tree. I'd just like you to ignore everything else on the slide for a minute and just concentrate on the fault tree on the left. This is our safety artifact. This is what the safety team could have developed to be able to show that you can't get to that commanded excess insulin infusion. And for those of you who are unfamiliar with the semantics of a fault tree, basically it uses and OR gates, and the objective is to prevent reaching to the top level event. So what you could have here is the different ways that you reach that pump commanded to infuse more insulin than user intended. That's linked to this G12. So the safety team could break that down into the various ways that that event could occur, while simultaneously the security team are developing an attack tree. So attack tree uses very similar semantics to the fault tree and was actually developed as a derivative of fault trees. But the difference with attack trees is that you have, or it's possible in this version of them, to have the mitigations embedded into the attack tree itself. So here we have defense nodes as well as the top level attack. What the security team, because this link was established beforehand, the security team can know that actually malicious issuing commands is linked to an event in the safety domain. So they can develop the attack tree based on knowing what this safety fault tree is. And so our SSAF link is particular attacks linked to particular failure modes or faults in this case. But as I said before, this requires a lot of understanding about the system and the individual analyses in order to be able to make those kinds of links and argue over them. But the advantage, why would we go through this trouble? What's the advantage of doing all this extra work? The advantage comes in where the previous approaches that I was talking about, FMEVA, STPA-SEC, CRAF, those weren't very conducive to update. But creating these links in model form mean that when we get to step 5, updating the model, particularly during operation, we can know which attacks failure modes are related to safety consequences. So being able to make these links here, these are the SSAF links, enables us during operation to more quickly understand the implications of, for example, new vulnerabilities or making changes to the system, such as patching. Whilst it doesn't give us necessarily the actions we should take, it does give us context to understand what the consequences are. And this is important because security during operation tends to change a lot more quickly than safety. So, for example, new vulnerabilities are discovered for particular systems almost daily for safety critical systems. So I have an example of that here. So a researcher discovered 3 such vulnerabilities for the one-touch ping. And they're quite big ones. I didn't quite understand why this kind of system was created with such glaring weaknesses. But the 3 vulnerabilities were that when the remote was being configured with the delivery part of the system, communications were sent in clear text. So it meant that if an attacker were to gain access to those communications, they weren't encrypted. The second is that it was quite weak pairing between these two at startup when they were linked. And the third is that there was a lack of replay attack prevention. So those 3 together meant that an attacker could not only gain access to the network, but replay instructions in order to get information, for example, from the remote, but that could lead to excess insulin. So with these three new vulnerabilities, what it means is that this guy over here, if we have a new vulnerability, we could link it to a new attack. We know what failure modes this attack is related to, and so we know what hazard it's related to, in this case, hypoglycemia. And then we know the effects on patient safety. So that, at a base level, is the idea of creating not only the technical risk argument for safety, security, co-assurance, but also modeling or explicitly modeling those links. But before I move on to the next part, what we've been looking at is what I've been calling a traditional system. So this has had no autonomous decision making and already has had a level of uncertainty that we need to explicitly reason about. So one of the challenges that we've found when considering autonomous systems, so in this case, it's a robotic system that's used in a healthcare setting or in one of our AAIP demonstrated projects. The idea is not only for insulin, but electrolytes and other chemicals that a patient might need. Those are autonomously monitored and delivered to the patient to improve patient care. So now we have increased hazards depending on the type of chemical that's being delivered, but also the uncertainty related to the types of attacks, the new types of attacks that are introduced by this autonomous system. So I won't talk through these just yet because I'm very conscious of the time, but we've been able to link the types of attack paths with autonomous system specific hazards. So for example, H08 was a very big one, which is forced operator handover when they're not ready. So a common claim in safety arguments for autonomous systems is that the operator will have sufficient situational awareness to be able to take over and mitigate any hazard that is present. And this is just another example. And again, we see that H08 is present. And this is to do with the physical manipulation of the supply chain data for training the algorithm that the autonomous infusion pump is linked to. So those are our initial findings for the autonomous infusion pump. So we know that there are new security risks that impact safety. So therefore, the uncertainty problems that I mentioned at the beginning are even more difficult. And we also know that there are greater demands on the competence and skills that the human operator needs. So the difference in what they're expected to do and know is actually greater in this case. But an important thing to note is that actually the last 2 points go beyond those technical models and technical approaches that I was mentioning. They deal with the human operator and uncertainty, and that can't be captured in, for example, FMEVA or STPA-SEC. So actually, we need a separate confidence argument to be able to convince ourselves and potentially regulators that these have been addressed. I don't think I have time to go through this, but I'll be happy to talk through with anybody who's interested. To be able to address those socio-technical problems, I've also created the socio-technical model, which is part of SSAF, and that recognizes that actually not all our arguments can live on this level. So on the technical risk model level, they actually have to have a socio-technical level that sits on top of it. And very similar to the technical causal model, we have an influence model for the socio-technical factors. So some of the ST factors that we look at are conceptual. So what do we mean by loss? What do we mean by adversary? But also things to do with the structure, process, people, and technology. So for people, I've already mentioned competence, but also what are the regulatory structures that we're aligning safety and security in, and what are the tools that we're using? So these could be conceptual tools or actual implemented tools to be able to do that. And this just gives a bit more detail about some of those socio-technical factors that I was talking about. And so the implications of using SSAF means that we can get through life co-assurance and not just a snapshot analysis to argue that our safety and security have been aligned for not only traditional systems, but autonomous systems. It also means that we can preserve the expertise and knowledge and practices of safety and security, but have a way of bringing those together and have confidence that that information is being exchanged. But an important thing is that it makes the safety security arguments explicit so that we can provide information, explicit information about the argument that we're making. So as part of ongoing work in the AAIP, we're actually trialing this approach, the safety security approach, not only for the autonomous infusion pump, but for industrial manufacturing. So this is a welding robot that works collaboratively with a human operator to weld particular parts for example, aircraft during the manufacturing process. And the objective of this research is to see if there's any overlap with the highly socio-technical environment that we had in the healthcare setting. And these are just a few of the further open questions that we're hoping to address. So particularly, how do we decide when those synchronization points are, and how do we trigger them? How do we make those trade-offs? So actually, I've drawn the models quite simplistically, but there is a lot of negotiation and trade-off needed at those synchronization points. And particularly important for autonomous systems is how do we deal with post-incident information and activities? So for traditional safety, we have forensic standards. For security, we also have forensic standards, but actually nobody has drawn the overlap yet. How do we preserve both safety, or how do we meet both safety and security goals after an incident has occurred? Right, so in conclusion, there's a lot of overlap between safety and security for both traditional and autonomous systems, but we need to be able to explicitly argue about them. And one of the biggest problems is the uncertainty introduced not only by the intelligent adversary, but also the uncertainty introduced by autonomous systems. Thank you. I'm sorry I've gone over. Are there any questions?